I'm Dr. Comprin, head of the Mechanical Engineering Department. Sometime next spring, you'll have to make a choice of which engineering curriculum you would like to continue with before you can go on to the sophomore year. The purpose of this little lecture is to give you some idea of what mechanical engineering is all about to help you make an intelligent choice. If you've already made a choice, I hope you will pay attention anyway, because you really should know what all engineers are doing. To help you with this choice, I'd like to start out with some general remarks. I'm certain that by this time you have had a number of definitions of engineering, but I'd like to bother you with one more, a very simple definition. In the end, engineering really is design. It's not just mathematics or science or engineering science or whatever. The end result is design. And as you ponder the question of what kind of an engineer you want to be, you should think in terms of what sort of things would you like to design? What are you most interested in? One of the problems we have is that many times we focus on the differences between one engineering discipline and another. I'd like to call your attention to some of the similarities. Take a look at this. Credits common to all engineering students, 45%. Most of those are not even in the College of Engineering. You're going to take almost half of your courses in the College of Arts and Sciences. You notice here that the credits taken only by mechanical engineers constitutes 31% of the curriculum. This is pretty much true for all of the engineering programs. And so what you should be focusing on here right now is all the things that are common amongst the various branches of engineering. So maybe that choice is not as difficult as you want to make it out to be. After all, one of the things about engineering is to be adaptable, work in many different fields, and there is where I think the mechanical engineering program has a definite advantage. Some of the things that mechanical engineers work with are very obvious, of course. One might think of automobiles and trucks. Actually, it goes a little beyond that. We deal in propulsion in a more general sense. Jet engines, gas turbines, locomotives, all those things, part of the general area of propulsion. That's a mechanical engineering subject. Heating and air conditioning, that can range from anything to cooling a very large building, to a room air conditioner, to perhaps even a space suit for one of those astronauts who wants to walk around out there in outer space. We deal with mining machinery. That's a big business in this part of the state of Virginia. Farm machinery, automated production equipment, that includes machine tools and robotics, textile machinery, power plants, power generation, acoustics, noise control. To give you a little better idea what this is all about, I'd like to take you now on a short tour of some of our facilities. Biomedical engineering is an option that's available to engineering students in all departments. However, about 85 to 90% of the students that elect this option are in mechanical engineering. Our laboratory is run by Dr. Lee Arp, who's here with me now, and he will give you a little explanation of one of the things he's been working on. Lee?
Thanks, Dr. Comprin. This is one of many devices, but it'll give you an idea of the practical nature of our work and our trying to use engineering to help people. This is a demand type oxygen flow controller for treating chronic respiratory distress, primarily in adults. Normally, oxygen is delivered to a patient through a nasal cannula or a face mask. Oxygen is flowing at the rate of 2 to 6 liters per minute continuously, 24 hours a day, 7 days a week, as long as the patient's in therapy. That amounts to an awful lot of oxygen, and it's very costly. This device will reduce the amount of oxygen required for treating these patients by 65%. It's a very simple concept, not very easy to execute, but a simple concept. We turn the oxygen flow on while the patient is inhaling and shut the oxygen flow off while the patient is exhaling. Inhalation ratio inhalation to exhalation ratio is about 1 to 3. We have oxygen flowing 1/3 of the time and oxygen turned off 2/3 of the time, thereby saving 2/3 of the oxygen. The little box, white box you see here, is a prototype. It has alarm systems, blinking lights for warning when the oxygen is flowing, when it is not flowing. That's the first prototype. Here is a production model of the circuit. The unit will be placed into production this November, and you can see how it's been shrunk down using integrated circuit techniques. We combine electrical, mechanical, hydraulic, all of the different fields working together in biomedical engineering. We define biomedical engineering as a multidiscipline approach to the solution of medically oriented problems by biologists, life scientists, physicians, engineers, all of us working together. Come join us. We'll have a lot of fun.
We are now in our department's computer-aided design laboratory. What you're looking at here is a $2 million IBM CAD/CAM system. The group of students in here are mostly seniors in mechanical engineering who are doing their homework for their next class. The whole complex here includes about $3 million worth of the latest computer hardware for doing computer-aided design and computer-aided manufacturing. Here's the lab director. He's going to explain to you one of these projects.
Thank you. And what you see here is a super graphics workstation. It's driven by a Sun processor that runs at approximately 10 MIPS, and it's connected to a Raster Technologies workstation that does real-time shaded image graphics. You see an image of the space shuttle shown here, and that's made up of approximately 8,000 polygons being shaded and rotated in real time. This image is also described with the new international graphic standard called FIGS, Programmer's Hierarchical Interactive Graphic System. And this machine runs FIGS instructions in native mode. Here you see a model of the space station. We can zoom in on details. Improve the resolution of the model. All in real time. One final model here.
We need to move on, Arvid. We've got a few more things to look at. If you find this interesting, pay attention, keep your eyes out for our announcement of an open house. We're going to invite you all to come by and take a detailed look at this equipment.